So today we're going to learn about log functions. So logarithms at first might sound pretty complicated, but they're actually very simple. So consider the equation a to the power of what equals b. That's basically saying to what exponent we have to raise a to get to b. We can rewrite that as log base a of b equals what. So in it, a is the base, b is the result of the equation, and the question mark is the exponent that you need to raise a to get to b. Logarithms have many useful applications, like for example, if you see this equation, y equals a to the power of x, we can use logs to solve for x. So, there are many log functions which I use in life. For example, the growth function, which is y equals a times 1 plus r to the power of x. R is the rate of growth and a is the initial amount. The opposite of this function would be the decay function, where it's y equals a times 1 over 1 minus r, to the power of x. R is the rate of decay, and a is the initial amount. It's basically the same thing, just that in one, the r is subtracted, in the other, the r is added. There are some special types of growth and decay functions. For example, the half-life formula, which helps us find how much of an element remains after a certain period of time of nuclear decay. So, in it, a is the amount left, t here is time, a of 0 is the initial amount, and h is the half-life. There's also the compound interest formula for finance. In it, a is the amount after t years, t is time in years, p is the initial amount, r is the interest rate, and n is how many times per year interest is compounded. Now, as n goes to infinity, something very interesting happens. Sorry for that. So, as n approaches infinity, this equation can be reduced to this, to the number e, which equals approximately 2.7182, and it keeps going on and on and on. Now, there are many properties of logarithms. For example, the equation log base a of b equals c can be rewritten as a to the power of c equals b, as we already learned. Then we have the exponent property. When we have log base 10 of b to the power of a, we can bring that exponent down and rewrite it as a times log of b. Then, when we're subtracting logs, for example, log of a minus the log of b, we can rewrite that as the log of the results divided. So, that would be log of a divided by b. Since that is true, the opposite obviously is true. So, we can rewrite an addition statement of log of a plus the log of b as the log of a times b. Then, there's finally a very useful property, which is the change of base formula. In it, you can grab a log of any base you want and make it into any other base. So, all you have to do is use the same base and do the log of the result divided by the log of the base. Now notice, it's not just the log, a single log of the base divided by, of the result divided by the base, it's two distinct logs, which one is divided by the other. And we can provide this as anything we want. We could rewrite it even as the natural log of b divided by the natural log of a. Then, when using natural logs, much like the property we saw earlier, we can rewrite the natural log of b equals c as e to the power of c equals b. Now, it's important to remember that we can only take the log of positive numbers. And this is because there's no exponent you can raise something to get a negative result. That just doesn't make sense. Some special logs are the log base b of 1 always equals 0, because anything to the power of 0 always equals 1. Then we have the natural log of e equals 1, which is logical, because what do we need to raise e to get e? Well, 1. And then, of course, we have the log base b of 1 over b, that equals negative 1, because what do we need to raise b to get 1 over b? Negative 1. So, to practice this, we can try solving some log equations without calculators. So first, consider the equation 4 times log base 3 of 2 minus 2 times log base 3 of x equals 1. So, first, we're going to raise 2 to the power of 4 using the power property, which gives us 16, and we're going to rewrite this as x squared, again using the power property. Then, of course, we can combine this since they have the same base, and that will give us 6 log base 3 of 16 over x squared. Now, we know, of course, that we can rewrite this as an exponential formula, which means that 3 to the power of 1 equals 16 over x squared. We can then solve for this, multiply x by both sides, divide by 3, and then take the square root. Another example. We can solve exponential logs which involve natural logarithms. So, let's solve 7 to the power of 3x equals 20. So, we first take the log base 10 of both sides. That allows us to bring the 3x down and multiply it times the log, which gives us 3x times the log of 7 equals the log of 20. We then just solve for x by dividing both sides by 3 times the log of 7. Now, of course, if we really wanted to, we could find out what exact number this is, but of course it's going to be a very horrible number with lots of decimal points, so it's probably just easier to leave it in this format. Now, let's try and solve the log of 3x plus 1 equals 5. Okay, so first we can try rewriting this as an exponential. So that means that 10 to the power of 5 equals 3x plus 1. We can obviously calculate this, which gives us this statement. We then subtract 1 from both sides and divide by 3, and we get that x equals this. Okay, let's try this other problem. 2 times the log of x minus the log of 3 equals 2. Okay, so first we're gonna transfer this this 2 back into the x, and we're gonna raise this x to the power of 2 because, of course, the quotient property. Then, since this is being subtracted by this, we can rewrite that into a single statement, which is x squared divided by 3 equals 2. Okay, we can rewrite that as an exponent, which is 10 to the power of 2 equals x squared divided by 3. We can, of course, find that this equals 100, multiply both sides by 3, and then square root them, and we get that x equals plus or minus 10 times the square root of 3. Okay, now, this is another example. Use natural logs to solve 7 times e to the power of 2x plus 2.5 equals 20. So, starting out, we, of course, rewrite our statement to be organized. We then subtract 2.5 from both sides. We then divide by 7. And then we can take the natural log of both sides. Now, when you think about it, what power do you need to raise e to get e to the power of 2x? 2x, of course. So that simplifies into this. And then the other side, you just have the natural logarithm of 2.5. You can divide both sides by 2, and you get that x equals the natural logarithm of 2.5 divided by 2. Okay. So now, this is how you evaluate logs without a calculator. So for example, what happens if we wanted to know what the log base 2 of 4 equals? Or we could also say, by what power do we need to raise 2 to get 4? Many of you, of course, will immediately tell me 2. But it might get a little more complicated at times. So, remembering the property that we found before, we can rewrite any logarithm as an exponential statement. So, for example, we have, of course, the log base 2 of 4 equals what? Which equals 2. Then, what happens if we have the log base 5 of 125. So what power do we need to raise 5 to get to 1 over 125? So of course, if we try raising 5 to the power of 3, we get that equals 1 over 5 times 1 over 5 times 1 over 5, or 1 over 5 to the power of 3, which gives us 1 over 125. Sorry, by that I mean to the power of negative 3. Now, we have here some problems for you to try. Try all of these, and after that, we'll show you the answers. You can pause the video now to try. Okay, hopefully you tried all of that, and here are the answers. So number 1 is this, and so forth. Pause the video now if you want to check your work and look at the answers. Okay, so this is what you should have learned from this video. To solve the half-life, growth, decay, compound interest, and continuous interest problems using those formulas, the properties of logs, solving logarithmic equations without a calculator using the properties, solving exponential equations involving logs or natural logs, and evaluating logs. Thank you very much for watching. Here are the credits.